Hey guys, this is Mrs. Harbin and this is Algebra 2. Today we are looking at Section 5.5, Complex Numbers. Now I've been having a little bit of technical difficulty with my slides here, so everything hopefully will work this time around. Our biblical integration for our unit is this. Biblical imagery of parts belonging to a whole helps us to see that some numerical groupings can be broken into specific separate parts. And today we're going to look at the parts of complex numbers. Our lesson objective for today is that you, the student, will graph complex numbers on a complex plane, find absolute values of complex numbers, simplify powers of I, and add, subtract, and multiply complex numbers. So we are going to graph, we're going to find, we're going to simplify, and we're going to do some computation with our complex numbers. Now, we talked about complex numbers at the end of the last lesson, and a complex number, represented by z here, is a number that can be expressed in the standard form z equals a plus bi, where a and b are real numbers and I equals the square root of -1. Now, I've actually created a playlist on imaginary numbers. You can head to my YouTube channel, click on that imaginary numbers playlist, and you'll get a whole history of imaginary numbers, where they come from, where this I comes from, and hopefully a better understanding of complex numbers. Imaginary numbers are one type of complex number. And imaginary numbers are numbers of this form, a plus bi, where b is not equal to 0. So you see over here on the right, we've got some imaginary numbers. And imaginary numbers can be further categorized into pure imaginary numbers. That's where a equals 0. So all you're left with is the bi part. So 3i is a pure imaginary number. 6i is a pure imaginary number. So imaginary numbers are one type of complex number. The other type of complex number is the real numbers, and real numbers occur when b is equal to 0. So in our complex number 8 plus 0i, because I is being multiplied by 0, we're left with 8, which is a real number. So we've got two types of complex numbers, imaginary and real, and underneath imaginary, we have this pure imaginary number. All right, so we can identify now, hopefully, imaginary and real numbers, these complex numbers. Let's move on to graphing them, simplifying them, and doing some computation. Complex numbers can be graphed in a plane called the complex plane. The complex plane is similar to the Cartesian plane in that there is a horizontal and a vertical axis. However, in the complex plane, the real component, the real numbers, go along the horizontal axis, much like our number line, and our imaginary numbers, or the imaginary component, will go along the vertical axis. So a complex plane looks like this. We've got our real numbers on the horizontal axis. We've got our imaginary numbers on the vertical axis. And to graph a complex number, we take our real number, which in this case is -3, and go over to -3 on the real number axis. And then our imaginary number, which in this case is plus 2i, so we go up 2 on the I axis here, and we graph that point. So this is our -3 plus 2i. Now you should see that if we were to connect these points along the real number axis, the imaginary axis, and then create a line that goes from the point we graphed back to the origin of 0, 0, you've got a right triangle. And this right triangle can help us find out some more information about complex numbers, because we can use a little thing that you guys like to talk about all the time, the Pythagorean theorem, to help us find the distance between this complex point and the origin. To do that, we need to know about absolute value. The absolute value of a complex number, z equals a plus bi, which is also called the modulus, is the distance from the origin to its graph in the complex plane. So if we go back to our previous example, the modulus of this complex number is root 13, or the square root of 13. That is the distance from this point to the origin. The modulus there is square root of 13. So, but talking about absolute value, then we're going to have this formula. The absolute value of z, represented here on the left, is equal to the absolute value of a plus bi. And because of what we know about the Pythagorean theorem, we know that a squared plus bi squared would equal that modulus. So we can take the square root of a squared and b squared to find out that third side of the triangle, the distance from the point to the origin. Let's take a look at 4 minus I, and let's find its absolute value after we graph it. Okay, first of all, we need a imaginary plane here, and this is going to represent our real numbers. Not imaginary plane, the complex plane, sorry, and this is going to represent our imaginary numbers. So we're going to go to the right 4, 1, 2, 3, 4, and then we're going to go down 1 I. So that would be this point right here. We could connect our points and create this right triangle where this is 4 and this is negative I. So we know to find the modulus, we would take 4 squared plus negative I squared, and that would equal our modulus squared. That's going to find this distance here. So the absolute value of 4 minus I equals the square root of 4 squared and this negative I squared. And negative I is equal to negative 1. 4 squared is 16, and negative 1 squared is 1. So we end up with the square root of 17. So our absolute value of 4 minus I is the square root of 17. That's also our distance from this point in the complex plane to our origin. Again, that is called the modulus. Now let's talk about some computation. So when we're adding, subtracting, multiplying, and dividing, we can add, subtract, multiply, and divide complex numbers. Two complex numbers written this way, z equals a plus bi and w equals c plus di, are equal if and only if a is equal to c and b is equal to d. So essentially, my real number must be equal to my real number, and the coefficient of my complex number must be equal to the coefficient of my complex number. So we can see that these two, my pure imaginary number. So we can see that these two complex numbers are equal because their real numbers are equal, as are their imaginary coefficients. Both of those are equal, so these two complex numbers are equal. When adding or subtracting complex numbers, we would add or subtract the real number and add or subtract the imaginary component as well. If z equals a plus bi and w equals c plus di, we would add or subtract, depending on the sign, our real component and add or subtract our imaginary component. So we would add a plus c and add b plus d in front of our I here. If we're subtracting, we would take a minus c and b minus d. We would then combine any like terms that need to be combined to simplify. To multiply complex numbers, we can apply the distributive property or the FOIL method. The tricky part is remembering to simplify the I. As a quick point of reference, I to the 0 power is 1 because anything to the 0 power is 1. I to the first power is just I squared is negative 1. Remember that I is the root of negative 1. So I squared is negative 1 squared. And the square just undoes the root, which leaves us with negative 1. I cubed would be I squared, negative 1 times I, negative I, and I to the fourth equals 1. And we'll take a look at this in a little bit more detail here in a minute. There's also a chart for your reference on page 207 of your book. So if you want to have that handy, write that in your notes. That's also on page 207. All right, so I to the first equals I, and I equals square root of negative 1. I squared then is negative I. If you can focus on these two, then we can derive any others. I cubed, which is I squared times I. If we break that exponent apart, that gives us negative 1 times I. which is just negative I. And I to the fourth is I squared times I squared. Well, I squared is negative 1 and negative 1. Negative 1 times negative 1 is 1. We can then keep on going following that pattern. I to the fifth is I to the fourth times I. Well, I to the fourth was 1, and 1 times I is I. And you should notice then that our pattern will start to repeat. And because math has so many patterns, we can use shortcuts to help us figure out more complex problems. So let's simplify 5i times 3 plus 2i. Using the distributive property, we would get 15i plus 5 times 2. 5i times 2i would be 10i squared. We know that I squared is the same thing as negative 1, so let's substitute that in. And after simplifying, we get negative 10 plus 15i. All right, this time let's multiply our complex numbers using the FOIL method. First, outside, inside, less. We get 4 times 2, 4 times positive 3i, negative 2i times 2, and negative 2i times 3i. And we end up with these terms. Let's combine like terms and substitute where we can. Doing so gives us 8 plus 8i minus 6 times negative 1, because we know I squared is negative 1. When we simplify again, the most simplistic answer we can get is 14 plus 8i. Remember this, a product of conjugates is a difference of squares. So go back to what we've been looking at in factoring. If we have a plus b times a minus b, we can take a shortcut and write a squared minus b squared. Or if we're factoring and we recognize that what we're factoring is already in a squared minus b squared, we can go ahead and factor by writing our two factors as a plus b and a minus b. So that was our difference of squares. And we said that a sum of squares we couldn't really factor without imaginary numbers. So let's take a look at that now. A product of complex conjugates is the sum of squares. A plus bi times a minus bi equals a squared plus b squared. This allows a sum of squares to be factored. So if we do see a sum of squares that we need to factor, we can factor it, but we're going to have to use our complex number here. Okay, a complex number factoring a sum of squares, a squared plus b squared, would take us back to this a plus bi and a minus bi as our two factors. All right, let's multiply this complex numbers using first, outside, inside, last. Let's FOIL. Doing so, we would get 9 minus 15i root 2 plus 15i root 2 minus 50i squared. Now, there's a couple of steps that we took to get from here to here. We would take the 5 times 5, the I times I, and the root 2 times root 2. 5 times 5 is 25. I times I is I squared. And root 2 times root 2 is just 2. That's how we ended up at that 50i squared. Combining like terms and substituting in where we can, we get 9 minus 50 times negative 1, because we know I squared is negative 1. These two inside terms cancel each other out, which leaves us with 59. So we could FOIL that. Or, if we notice that these are conjugates, we could just take our A term, which is 3, and write 3 squared, and our B term, which is 5i root 2 squared. And that would give us 9 minus 50i squared, which would lead us to 59, the same answer. So you can FOIL, however, recognizing conjugates and recognizing these patterns might save you some time. All right, let's factor x squared plus 4. We've got a sum of squares here, so we're going to use that rule that we just learned. Our x plus 2i and x minus 2i. All right, guys, if you have questions, be sure to ask me next class.